Hello, myself Naveen Kumar Saini in the course Electromagnetic Field Theory. Today we are going to start Unit 3. So few important topics we have covered in the Unit 2, okay, which was totally based on the electrostatic field. Now we come to the next topic of that is the magnetostatic field. So there is an analogy of between the electrostatic and the magnetostatic. Some analogy we will discuss it here so that the things will be easy to understand in future as well. So here in the electrostatic field, we are characterize the terms that is E and D, right? So where the relation was D is equal to epsilon E, this which was discussed in the just previous slides or the previous lecture as well. So here in this chapter which we are going through it in the magnetostatic field, there is a when we have the electric field, then corresponding to that we have the H. So E is what? Electric field intensity, and H is what? This is the magnetic field intensity. Then second is the D. This D is the electric flux density, and corresponding to that the analogy here is the B. This is the magnetic flux density. So these students sometimes get the confused in that. So every time they write mix of E, H, D and B, right? So things must be clear to all of you. E electric field intensity, H magnetic field intensity, and then we have the D in the electric field, that is the electric flux density, and corresponding to that into the magnetic field we have the B, that is magnetic flux density. So the relation here B is equal to mu into H. So epsilon is the permittivity, mu is the permeability. So epsilon represent the medium, the electrostatic field for the materials in the electrostatic field, and a mu permeability for the material in the magnetostatic field or magnetic materials. So here the distribution of static and stationary charges which are produced in static electric field. So here in the magnetic field we have the charges which move at constant rate. Direct current or DC. In static magnetic field is produced magnetostatic field, right? So when we have the constant charges which are not movable, so electric field will be appeared in that. For the stationary charges, when we have the charges which are moving in nature, so in that way the magnetic field will be generated. So the static magnetic field are also produced by the stationary permanent magnets. So these are very basic things which every students know when they go through the physics part of in the physics as well in the first year. So I believe that each one of you are a little bit aware about that, what is the generation or what are the sources of the electric field and the magnetic field. Okay, so these are the analogy which I have gone through from that book as well, from Sadiko book. So please go through it. It's very nicely described there. So electrostatic field which has a dual equation for magnetostatic field. Basic laws here we have the electric field, that is the Coulomb's law, right? Coulomb's law is there, and corresponding to that analogy in the magnetic field we have the Biot-Savart's law. Okay, so Biot-Savart's law here, Coulomb's law for that, and corresponding to that we have the Gauss law, that is D dot ds is equal to q enclosed, and Ampere's law we have the H dot dl is equal to I enclosed. So for that we have the Gaussian surface, and for this we have the Amperian surfaces, right? Amperian path, sorry. So here we have the Amperian path for the case of for this equation of Ampere's law. Forces in the case of electric field, F is equal to Q into E, and here we have the Q U cross B. Because the charges are in motion, so in that case it will have some of the velocity, so the force will be into it, and the B is the magnetic field which is generated by the any other source. Okay, so the source element for the electric field is the dq, and in the case of magnetic field this is the du, that is idea. So we will cover all this topic is okay in future. So field intensity is equal to V upon L, and here we have the H is equal to I upon L. Flux density D is equal to psi upon D, and B is equal to psi upon S as well, psi upon S in both the cases, but when we have here we have the fluxes and into the electric field and the magnetic field. Formula is same. but the significances are different. So, relationship between the fields D is equal to epsilon E and B is equal to mu H. Here we have the potential E is equal to minus del V. When potential is known to us, then we can calculate the E, or when we have the line charge. So, for that the potential will be rho L dl upon 4 pi epsilon naught R. Here we have the two types of potentials in the magnetic field. When one is we have the static field because of the charge, presence of charge. Second, we have the vector field when the charges are in motion. Okay, so two potentials are there in the magnetic field, that is the scalar field and the vector field, but there is a scalar field in the case of electric field. Flux, that is flux is C into V. Here we have the L into I. So, C is the capacitance in which the electric field energy will be stored, and in the magnetic field we have the inductors in which the magnetic field energy will be stored. Then we have I is equal to C dV upon dt and V is equal to L di upon dt. Here energy density formula which is given WE is equal to 1 by 2 D into E. This is energy density, so the unit for this one will be nothing but joule per meter cube. Okay, similar to that we have the energy in the case of the magnetic field, that is half B dot H. Okay, Poisson's equations which is given here in the case of electric field, that del square V is equal to minus rho V upon epsilon. Here del square A is equal to minus mu into J. So, these all are the analogy between the dual equations, or analogy between the electric field and the magnetic field. Okay, so now let's start unit 3 in efficient manner so that you can understand the things or the crux into that. First is the first analogy or into magnetic field as compared to electric field. In the electric field we have general law, that is the Coulomb's law. An analogy here in the magnetic field we have the Biot-Savart's law in the magnetic field. So, what it says that DH means the magnetic field. So, here that is magnetic field at some instant of point due to the line current. So, this is very simple. If we have any of the line current, so in which the current is flowing into it, and we want to calculate the magnetic field at this point. So, this is proportional to the ideal current flowing into this element and inversely proportional to the distance from this point to this point, right. So, this is the R square, and again it is proportional to the sine of the angle between the current flowing into this direction and the distance R in this direction. So, this is the alpha. So, DH is proportional to ideal sine alpha upon R square. So, here we can use the proportionality constant, that is K. So, DH is equal to K ideal sine alpha upon R square. So, K is here, that is 1 upon 4 pi. So, in the case of Coulomb's law we have the K, that was the 1 upon 4 pi epsilon naught, but we have the 1 upon 4 pi. So, when you put this value here, then in this case DH will be ideal sine alpha upon 4 pi R square, right. So, this is the Biot-Savart's law. In the statement we can go through. Biot-Savart's law states that the magnetic field intensity DH produced at a point P, so this is the point P, by a differential current element. So, IDL is the differential current element, is proportional to the product IDL and the sine of the angle alpha between the element and the line joining P to the element, right. This is the line joining, and is inversely proportional to the distance R between P and the element, and its direction can be obtained by right hand screw rules, right. So, the direction of this one we will discuss about that, but the definition must be clear to all of you about the Biot-Savart's law. So, here the neatly explained diagram here which shows the one current is flowing into this conductor, and we are taking one of the element here, DL is there. So, in this DH we can find out. So, what is the rule for finding the direction of that is, you can hold this direction like this, and the direction of these fingers are representing the direction of DH. So, we can say if we want to find the magnetic field at this point, so we can see the direction of this one is downward, right. So, this is direction of E. So in this case, the direction of is inside the board, right? So if I want the electric field at this point, so what is the direction of H? So when you're holding again like this, so this thumb is in the direction of current, right? Like this. So in this point, the magnetic field is coming out from this board, so we can represent it like this dot, right? So here this inside the board, this one is the right hand, this is outside the board. So here why we are saying all this, because we have the sine part here, sine alpha. Sine alpha, when this sine alpha comes, it comes when we have the cross products, right? And cos alpha, then when we have the dot product. These things must be clear to all of you. Sine alpha is for the cross product, so it means the cross product will be what? This is the cross product between the IDL and the AR. So this is the direction of AR, this is the AR, and here we have IDL cross AR. When we calculate this, so this is equivalent to this, because IDL mode of AR is 1 sine alpha, right? So in place of AR, we can put a vector R divided by mode of R, right? So we can put like this, and here IDL cross vector R divided by mode of R cube. Okay, so it can also, direction of magnetic field can also be find out with the help of the right hand screw rule, right? So this right hand screw rule, the same thing is there which I have just explained, right? So these directions of these fingers are representing the direction of H. Okay, like this. So we have to hold this current element like this. So direction of thumb. Okay, this is the direction of current. Okay, then here we are representing the direction of magnetic field again, H, which can be represented by the small circle, area circle, and with a dot which is representing the directions. If it is going out from the board, so we represent like this. When the things are going, direction of H is inside the board, so it is representing like this. Okay, so these complete things are representing the direction of the H, and this is very, very important, right? Okay, so for different current distributions, okay, so till now we have just covered talking about the current element. So in this first case is the line current, right? Second, when we put all these lines onto the surface, right? Suppose I have one, this is the one line current, second line current, third line current, fourth, fifth, like that. If we put onto the surface, so this surface will be act as the surface current, just like in the current when we talk about in electrostatic field, we distribute the charges onto the surface. We said this is a charge density or surface charge. When we put all charges into the volume, we said this is the volume charge density or the volume charge, right? Similar to that, when we have the line current, so line current is what? This is the one line in which the charges are moving in some velocity. So we say this pen will become the line current. And when we put all the different line currents all together onto the surface, onto a given surface or substrate, then we say this is the surface, right, or the surface current. Third one, when we have the same line currents and we put all these line currents into the given volume, right? So into the given pipe, like on the cable, when we put all the line currents, so we say this is the volume current, right? So here for that here the element is IDL, that is equivalent to the KDS in the surface current, that is also equivalent to the JdV into the volume current or the volume current, right? So here, as we know, the IDL we have derived from the Biot-Savart's law. So in place of IDL we can put the KDS or we can put the J into dV. So these three are the same, and the units for this is IDL. Unit for this one will be ampere meter. Here this is also ampere meter, this is also ampere meter. So this is the units for all these elements, right? So it means the unit for K will be what? This is the ampere per meter, right? And here J unit for this one will be ampere per meter square. Okay, so this is very, very important to know that current density for surface current density ampere per meter, volume current density J ampere per meter square, and here this is the ampere meter or the current is A only, ampere. Okay, So based on that, depends on what type of elements which we have, based on that we can find the value of H. Okay. So another very important topic in this unit third, that is the magnetic field due to the straight conductor. So for that, what we have the we can consider for finite length AB. So we have the one element, just like this pen, we have the this is the A and this is the B, right? So what my question is, I want to find the magnetic field at some instant, at some point P, right? So how to calculate the magnetic field at this point? So for that one, what we are taking the point P, and this is my line, in this is the current element A to B. So for that one, we will take consider the contribution of dH at the point P. So formula we will put it like the same as we have the Biot-Savart's law, ideal cross R 4 pi into R cube. So we can see that I is constant in that case, current which is flowing, this is constant, and here 4 pi is also constant. So what left? We have the dl. This dl will depend this in which coordinate system, Cartesian coordinate, cylindrical, spherical coordinate system. So for that, dl we can take care of. R is important. R is the distance from this element to this particular point. So we can put all this all together, right? We will use this equation. Okay, so what we require? DL. So just come to this point. DL is what? DL is in this direction of Z. So we can take the DL is equal to DZ AZ. Then we want the R. R is this one. And for that, what we are taking the projection at this point. So this is the origin, this is the rho, from here to here, this is the rho, this is R, and this is the Z. Okay. So when we have this one, so easily we know the direction of rho will be obviously rho in this direction, R in this direction, and Z in this direction. So this is the you can apply this vector calculus here. Rho is in this direction, Z in this direction, and R in this direction. So when we solve it, then we will get the R is equal to rho A rho minus Z AZ. So just put it all together into it. So DL cross R, you can take DL cross R, it will be equal to rho DZ A phi. So we have covered all these calculations of cross products of AX, AY, AZ, or A rho, A phi, AZ into the first lecture. So I suggest you, if you are not comfortable with this right now, so please go to the unit 1 lecture of coordinate systems. There I have discussed about the complete orthogonal system. Okay, so please go through it. Then these things will look very easy. Only the important point is this: if you know this into this topic, then into this lecture, rest are very easy. Please go through it. Then you will see that when you take the DL cross R, so AZ cross A rho or AZ cross AZ, what is that value? Obviously AZ cross AZ will be 0, AZ cross A rho will be what? A phi. So in this case it will be A phi terms. So rho dz A phi. So just put value this one into this equation. So expression which we got, this one, this is very important expression. Now this is the main expression now. So what we want to solve this integration, right? So for that, very simple cases we have covered in the unit. If you know, in the first year you have integrated the integration. So for that one, you assume some values for that, right? So take something like rho square plus z square, you can take tan square or something like that, or you can take the z is equal to rho cot alpha, right? So just put it, rho z is equal to rho cot alpha, then dz will be obviously minus rho cosec square alpha d alpha. So what is the alpha? Alpha is this one which is moving from A to B, right? So in this case, what we are assuming, we are taking the alpha 1 for the lowest part of this line current, and the alpha 2 for the upper part. So alpha 1 is this, alpha 2 is this one. So this alpha is varying from A to B. So that is why they have taken the alpha 1 to alpha 2, and we have put this all together into this equation. So when you are solving this one, then H will be equal to I upon 4 pi rho cos alpha 2 minus cos alpha 1 into A phi. So if we take it into the cylindrical coordinate system, so again this direction is what? This direction is phi direction, right? So automatically we will get the phi direction here. Again I am repeating, please go to my lectures from the unit number 1, where I have discussed completely in detail about the coordinate system. It will help you to understand all these basic things, right? Okay, so H is I upon this one, and here we have put tan alpha is equal to rho upon z, z is equal to this one. Okay, so 1 plus cot square alpha, cot x is equal to cot square x, cot x square x. So please, this is the trigonometrical formulas. So I believe that, and this is prerequisite for this EMFT. So trigonometrical formulas you must know, differentiation, integrations, and what is change of transformations. Okay, so in sine, cos, tan, cotec, cosec, sec, all these are very basic things which you must know. Okay, so here the H is equal to I upon 4 pi alpha rho cos alpha 2 minus cos alpha 1 a phi. So okay, so here, so let's have some of feel of this one, conductors. This is the one finite length A to B. Now if I want the semi-infinite means one point we must know at some instant and some point, and B will be in the infinite. So we can see if this A is here, the what is the value of alpha 1? If A is here, then alpha 1 will be increase, it is become 90 degree. When B is infinite, so it means this alpha 2 will be very small, tends to 0. So alpha 1 will be 90 degree, alpha 2 will be 0 in this case for semi-infinite, right? Just put all this value alpha 1 and alpha 2 here, then you will get the value of H at point P. Clear? Now, if I want the alpha 1 and alpha 2 in this way, so that we can find the infinite line, for the infinite line. So what will happen? For the infinite line, alpha 1 will be what? Infinite. So alpha 1 will increase up to here 90, then 95, 120, like that, up to 180 degree, right? So alpha 1 will be 180 degree and alpha 2 will be again infinite, it will be 0. Okay, so let's see what we have discussed. For the semi-infinite case, point A is now at the 0, 0, 0 at the origin, and the B is at the 0, 0 infinite. So in this case, when you put the alpha 1 is 90 degree and alpha 2 is 0, so H value will be I upon 4 pi rho A phi. Okay, so when the conductor is of infinite length, then point A will be at 0, 0 minus infinite, while B will be at 0, 0 infinite, and alpha 1 will be 180 degree and alpha 2 is 0. So we can see it here. Alpha 1 will be increasing because this A point is coming down. So as the A point is increasing, then alpha 1 value will be increasing. If A is going up, alpha 1 will be decrease. Okay, so when alpha 1 is increased, so when alpha 1 A is infinite, so what will happen? When A is infinite, so it means this point will be very near to the line. When it is very near to the line, it means what is this angle? This angle will become the 180 degree. Okay, so simply just put the 180 degree and alpha 2 will be 0. So when you put all this all together into the equation, in the previous equation which I have just discussed, cos alpha 2 minus cos alpha 1, so just put it, then the expression which we got about the H is equal to I upon 2 pi rho into A phi. So it will become the half of this H value. Okay, so we are simply using this one and we are putting the value of alpha 1 and alpha 2 into it for the semi-infinite and for the infinite case. So H value will become this much, I upon 2 pi rho into A phi. Okay, so this is one of the formula which you can go through, that A phi is equal to AL cross A rho, right? So AL is what? This is a unit vector along the line current, and A rho is the unit vector along the perpendicular line from the line current to the field point. Okay, so I hope this derivation is clear to all of you to find the magnetic field intensity for due to the infinite line current, and this is very important topic, and it comes in your UT exam very frequently. Every time in one way this question will be asked, or one of the numerical they can ask about that, right? So that this point I have discussed how the value of alpha 1 and alpha 2 is changing for the semi-infinite and for the infinite cases. One of the question you can go through it. It is very easy to understand. Just I want to give a feel of this question. What? That the conducting trigonal triangular loop which is mentioned here in the figure carries the current of 10 ampere. Okay, so one loop is there, this one you can say this is A, B, C and A. So this is the loop in which the current 10 ampere is flowing. Okay, so what we want the value of H at 005 due to the side 1 of the loop. So let's see, there is one of conducting triangular loop is there, right? And what we want the magnetic field intensity at 0.005. So where this loop is lying? This loop is lying on the x and y plane. It means this is lying at z is equal to 0 plane, right? And what we want the value of H. Suppose this is your origin and this above, this is your z. In the 3-dimensionally we can think of. So this is the z. So what we want the value of H at this point. This is what 0, 0, 5. So we want the value of H here. Clear? So what we want due to the side 1. This is due to the side 1. We want the value of H at this point. So how to calculate that? So this is very simple. Again we can apply this formula which I just said. We can apply this and simply we will put the value of alpha 1 and alpha 2. So we will put this value alpha 1 and alpha 2 into it because I is given to us. Okay, 10 ampere, 4 pi is given, 4 into pi, right? Rho is also given into it, right? So what left? Value of alpha 2 and alpha 1. That's it. If we know this, then the rest things are very easy to understand. So what is the value of rho? Important point is this now. Rho is what? So this guy have considered in this picture, this is equivalent to this. We have considered the loop 1. So this is the loop 1 and we have flipped it, right? So we have flipped this diagram into this. So when we have flipped it, then this z point becomes here. Okay, so this is the same which I have just discussed, that is 005. So this question become like this. This is a one line. Okay, alpha 1 is from the origin point, means as I said alpha 1 will be what? The angle from this point, right? Alpha 2 from this point. So alpha 1 for this point, alpha 2 for this point. Okay, you can compare it, alpha 1 and alpha 2, you can see. So here alpha 1 is this, alpha 2 is this one. Clear? Same thing is there. Only we have to find the value of alpha 1 and alpha 2. So see, rho is what? Rho is the distance from the line current to that point at which we want to calculate the magnetic field intensity. So this is the line current A, B and this is the point. So this distance, this perpendicular distance from this line will be the rho. So here this is a perpendicular line for this distance from the line, this is the rho. So it means that we got the 5. So rho is equal to 5. Clear? So rho is 5, 005 and this is the line, we want the alpha 1 and alpha 2. So when you put alpha 1 in the diagram, so alpha 1 will be what? By this diagram. So this is 90 degree. Clear? We can see it here. But what we want the alpha 2. How to calculate the alpha 2? Okay, what is this distance? 2. What is this distance? 5. So you can find the alpha 2. This is very simple now. Clear? So based on the trigonometry, you can find the alpha 2. So we will go through it. This is my formula which I said, I upon 4 pi rho cos alpha 2 minus cos alpha 1 a phi, that is valid for any straight thin line, right? This is very important point which you have to take care of for any straight thin line. Current carrying conductors alpha 1, alpha 2 and a phi are found as follows. Alpha 1, as I said, 90 degree, very much clear to all of you. Alpha 2, as I said, this is the 2, this is 5 and when you are solving this, it will become what? This is 29, right? 5 square plus 2 square, or you can say simply, if you got confused, 5 square plus 2 square, that is 29. Clear? So 25 plus 4, this is 29. So 29 is there, then cos alpha 2 you can calculate, that is 2 divided by root of 29. So this will become the cos alpha 2. So cos alpha 2, now we got cos alpha 1 we got, rho we have this value 5, just put it. Now the case is for the A phi. So A phi is nothing but the AL cross A rho. AL is the direction in which your current carrying conductor is lying. So AL is lying into the Z direction, X direction, I am sorry. This AL is lying into the X direction. So AL will become AX. So AL will become AX. A rho is what? A rho is the direction in which, at which we want to calculate the value of H. So at this point we want to find the value of H. Okay, so this is the rho direction. So here rho become the Z, so it will become the AZ. So A rho is equal to AZ. So when you put AL is the AX and A rho is the A rho, we can put the AZ. So in this case A phi will be what? Minus of A phi. So we can think about this. As I said here, this is the circle. We have AX, AY, AZ. When we have AX cross AY, we got AZ. When we have AY cross AZ, we got AX. When we have AZ cross AX, we got the AY. When we have the AY cross AX minus AZ, AZ cross AY minus AX, AZ cross AX cross AZ minus of AY. So same thing is here, AX cross AZ is minus of AY. So this formula, this method you must know how to calculate the value of cross product. Again repeating, if you are getting a little bit confused, so please go through my previous lectures in the coordinate system. This is a very important topic to understand, then only you can understand all these type of numericals, right? So please go through it, it will help you a lot. So H1 I upon 4 pi rho cos alpha 2 minus cos alpha 1 A phi. So in place of that, just put all value together. A is this one, rho is this one, cos alpha 2 is this, cos alpha 1 0, A phi in place of A phi you can put the minus of AY. So when you are solving, then H1 will be minus 59.1 AY milliampere per meter. So similar to that you can, okay, I hope this point is clear. So similar to that you can find the value of H at the point 005 due to segment 2, due to segment 3. Okay, so what you need to do for that, you have to find the perpendicular distance again for this point from this one. Okay, then only you will you can go through it. Same formula is there, only important point which is to take care about the rho, alpha 1, alpha 2. If you understood this point, then the rest of the things will be easy, but it will take little time because the practice is required for solving this type of numericals. Similar to that, we have the next question, that is a circular loop which is located at 0 x square plus y square plus 9. This is the circle equation, as we are aware about this, and which is lying, this circle is lying on the xy plane whose radius is 3. Okay, at z is equal to 0, carries a direct current of 10 ampere along A phi. Then determine H at 0 0 4 and 0 0 minus 4, right? So same procedure you have to apply. This is the assignment for you, please go through it. The formula which you have to take care, again dH you have to apply, dH, that is IDL. So I will take I will remove this portion so that things should not be confusing. So here just apply this formula, I dl cross r divide by that is 4 pi into mod of r cube. Is that clear? So what you require, dl, how you get dl? Dl is this one. What you require, r? R is this one. Same formula apply and just try this. This is the rho direction, this is the z direction. Apply the Pythagoras theorem, so apply that vector calculus in that, so that you can find the value of r. So same expressions are happened here, and in this way when you're solving this, just put the value all together. Same procedure is there, dl is there, r is there, and put it all together here. Then after solving you will get this expression. Okay, so by symmetry this will be this will be cancelled out. What will left? Only DHZ AZ. So in this way, this is again very important formula. Okay, go through it and put substitute the values of current, rho, H, then final final value you will get the 0.36 AZ, and B you can get it by placing H with the minus sign. Then the same value you will get at the below side, right, at this point. So the values at magnetic field intensity will be same at 004 and 00 minus 4. So this is the assignment for all of you. Please go through it. If you're finding any issue into it, please let me know. Thank you very much.